All right, so let me start again for the very last lecture hour, because I still have some stuff to cover. Right, so let's just see where we end. So I wanted to. So we were talking about the islands setup. Let me remind you quickly of what we saw this morning. Namely that in the pure gravity Laukwix-Maldacena derivation, we were working with an orbifold manifold that we drew something like this. So this is the orbifold manifold that we constructed. So it's a mathematical construct in this LM derivation, and it's a manifold with a conical singularity, namely a conical deficit here at the Zn fixed point. So we spent some time on showing that adding the brane allows for having this deficit here. So this is what we mean by saying that we add a brane to the Zn fixed points in this picture, because then we have that the action, meaning the gravitational action, but now accompanied with a brane action, gives you the gravitational path integral in a semi-classical approximation for this replicated theory. At least the pure gravity contribution, okay? And this is then what finally gave rise to the RT formula. So the pure gravity Laukwix-Maldacena derivation gives us a gravitational entropy, which is given by the area of the minimal surface sigma, which is dynamically determined by gravity itself, as being the surface that has a minimal area. Exactly there where we added the brane. So this was pure gravity Laukwix-Maldacena, and then we wanted to include bulk CFT matter in this derivation, and this we did by adding to that picture not just the brane for the pure gravity contribution, contribution discussed just now, but also I need more colors. Will this work? This is a twist field. That we had to add, again, to the same location, the Zn fixed point sigma, to include conformal matter in the bulk, such that the gravitational action in the presence of a brane, but also in the presence of matter, gives rise to gravitational path integral in the semi-classical approximation that now includes a matter contribution from this matter part of the action. And it's that matter contribution that gives rise to a matter entropy contribution to the total gravitational entropy. So a matter contribution which is an entanglement across the Zn fixed point sigma. So such a contribution to the total gravitational entropy SA. So that in total, we found this quantum extremal surface prescription. So adding the twist field is what I wrote as like this this morning. So that we had to add twist fields at the Zn fixed point for the replicated matter sector on the orbifold manifold. And so all of this is completely in analogy, this section here, to the original CFT replica trick, where we had a replicated CFT Lagrangian on the complex plane being an orbifold manifold with twist fields at the Zn fixed points, which in that case are the boundaries of the region A, which gives rise to ZCFT of n, which leads to the entanglement entropy of the CFT matter. Okay, so this is in complete analogy to that. And so the whole thing leads to the quantum extremal surface prescription that SA is the minimum of the area of the quantum extremal surface over 4G, which is from the brane contribution to the conical singularity of the orbifold, plus matter entropy, so let me call it across sigma, from the twist field contribution to the conical singularity. Okay? And this we then next apply to the island setup. Let me write the first picture here maybe, and then the replica manifolds will take some more space. So let's try this again, this cylinder. Okay. Okay, the cylinder is not closing so nicely, but you have a better picture from this morning. So this is the blue part is always the gravitational part of the island setup, and the green part is the non-gravitational part of the island setup. And then we chose this region A, which for physical reasons we now call region R for radiation, of which we want to calculate the entropy, so which we now call SR. So, as we discussed, the first way to try to calculate this is via a replica trick that doesn't care about this gravitational region yet, in the sense that we just create a replica manifold the way we would if A was living on a full green cylinder. So this is what we had on the board before. So these are my R regions or A regions, and there's the gravitational region in blue, which forms a replicated manifold, which we called Mn in Laukwigs-Maldassena notation for the gravitational replica manifold. And there's a non-gravitational part, which is the green part, which forms, in CFT notation, the replica manifold that we called R and comma A. And so the total replica manifold is, so because the island setup consists of a gravitational region and a non-gravitational region, a blue region and a green region. Also, our replica manifold consists of a gravitational part and a non-gravitational part, which I'll try to consistently put in blue and green. So the whole thing is our total island replica manifold. And so what we're drawing here is the option where we're working with the disconnected saddle in the gravitational region. Meaning that the replica manifold is only connected in the green region and not in the blue region. And so the idea was maybe there's a second saddle that should be taken into account, where also this gravitational region is connected. So say there is such another saddle, which is called then a ZN wormhole, which is defined as a gravitational solution that connects the gravitational regions of the replica manifold in a ZN symmetric way. And then you introduce some words and you say the region along which these gravitational regions connect we'll call the island. So as the analog of the region R in red, where the green copies connect. So you introduce the notion of an island, which is a region in the gravitational region, so in the blue part, along which the different replicas connect in the gravitational region, okay, in a ZN symmetric way. So let me add it to that picture maybe. There's a region here in the gravitational region now, which is called I, for islands. So I is the island region, and R is the radiation region. So the boundary of R are these points, the boundary of I are these points. Okay, and so these boundary points of the island, so I'm calling them points, but okay, in general they can be higher dimensional. The boundary of the island is then also Zn fixed points in the same way that the boundary of A or the boundary of R are Zn fixed points. And that means that the boundary of the island region takes the role of what we call sigma in the Laukes-Maldacena derivation. So in Laukes-Maldacena gravitational entropy language. So we have two island replica manifolds on the boards, one with a disconnected saddle in the gravitational region, one with a connected saddle in the gravitational region. Per definition, the gravitational region is dynamical and can decide by itself which one is dominating. And so the physics that tells us which one contributes to the entropy calculation is precisely this QES formula, which the derivation of which we sketched. Okay, so the quantum extremal surface is the one which minimizes this thing in brackets, and this comes from an action minimization thinking. So you can do the calculations and figure out which of these saddles dominates, and it turns out that indeed there is such a Zn wormhole solution that dominates at late times, and that saves you from the black hole information paradox and leads to actually a page curve instead of the ever-rising radiation entropy that you find if one is the only option. So let me add the orbifold pictures for both of these. So if this is a total island replica manifold, then the total island orbifold manifold will be one of these copies. Again, there's a gravitational orbifold for which we'll use the Laukes-Maldacena notation. And then there's a non-gravitational part of the orbifold manifold for which we'll use the CFT notation. So this is just C. So we have our radiation region here. And so in this first calculation, nothing's happening in the gravitational region. So all I have in my total orbifold is twist fields inserted at the boundary of region A, or region R, we called it. as in the usual replica trig derivation in CFT. So that's for saddle number 1. Now for saddle number 2, what is our orbifold, our island orbifold manifold? So again, it's one copy. So the non-gravitational region is the same. So we have our, oh my gosh. We have our ON in the gravitational region. We have C orbifold in the non-gravitational region. We have twist fields at the endpoints of the radiation region. And then in the gravitational region, we now have an island region called I. And the boundary points, well, I'll just keep calling them points. So the boundaries of this island, as I said, play the role of sigma in the gravitational replica trig derivation. Meaning, because there's gravity in the calculation, we had to add branes at sigma. So those are there on top, the blue circles that I added here. So I have branes at di, because in the orbifold manifold, in the Laukowitz-Maldacena derivation, I need to add branes at the Zn fixed points. This is just what I'm doing here. It's the same as on top there for in that figure. Yes?
Just to remind myself, I do this because I have this conical defect that I need to erase, right?
Yes, correct. So that's the point, and I'll summarize this right after this. But in the non-gravitational region, the orbifold is smooth at the endpoints where you put the twist fields. In the gravitational region, the endpoints of the island region are not smooth but have conical deficits. And the way to remember this is to put the branes there. But you also have to actually mathematically include them so that the action plus the action of the brane constructs the correct gravitational Z of n. Okay, so we've added branes, so the island setup is the gravitational region, the non-gravitational region, but also a matter sector, the CFT, that spreads out over the whole system. So we also have CFT matter fields contributing here. So we have to include bulk CFT, so it's quote-unquote bulk CFT matter in Laukowitz-Maldacena language. Meaning we have to add also twist fields to the endpoints di. So we have branes, and we also have twist fields. So the branes, indeed, because of the conical deficits there, will give us an A over 4G term in the radiation entropy, an area over 4G term, and the twist fields will give us a matter entropy term. In that radiation entropy. So let me give you the results. So I'll remove this maybe. From this replica trig derivation, including ZN wormhole connecting the gravitational region replicas, you find a formula for the gravitational entropy. No, sorry, you find a formula for the radiation entropy that has been given the name island formula. And so that island formula is the following. So this is called the island formula. So the goal is just to sketch roughly how the derivation goes a la Laukovic-Maldacena. Okay? This really is the picture that you're using. And so the A over 4G term is this phi over 4G here, because we're in a 2D, the whole thing is a 2D setup. So also this blue region is two-dimensional gravity, in particular some type of dilaton gravity, and in such a theory, the role of the area is taken over by the value of the dilaton in those ZN fixed points. Okay. So that's why we have a phi over 4G, but this is just our A over 4G from the branes at the boundary of the island. And from the twist fields, we have a matter entropy contribution. And so like in the RT formula, the location DI is dynamically determined by gravity itself to be the one for which the surface area plus the matter entropy is extremized. So this is the QES rather than the original RT prescription where you only minimize this part. Okay, and it's this island formula that that was shown to give rise to a page curve in this setup, and therefore solve that version of the black hole information paradox. So let me summarize where the conical defects are. So we called Mn plus Rn. Yeah, I need some more space. So so let's write it here. So we called Mn plus Rna, the whole thing together, we called the island replica manifold. And so it consists of this gravitational language here for the gravitational region and the non-gravitational notation here for the non-gravitational region. So you remember that the replica manifold has to be smooth. We had a whole discussion about this. This was the starting point of the Lauquix-Malacena derivation, is that the replica manifold has to be smooth. So this one is smooth. Then the replica manifold in the non-gravitational region has conical singularities at the boundary of region A. And those are conical axis singularities. So at dA, which we call now dr for radiation. So this was for the replica manifold, and then On plus C is what we can call the island orbifold manifold. And so it's the quotient of the replica manifold plus the quotient of the non-gravitational part of the replica manifold here. So like this. This is just C, so this is the one that's smooth. So it's smooth everywhere, but including at the dA points where you put the twist fields. And this gravitational part of the orbifold has a conical singularity, in particular a conical deficit. At dI. And so where the conical deficit is in the Lauquix-Malacena part of the orbifold manifold, we have branes plus twist fields. And here is where we have twist fields at dA. Okay, so this concludes what I wanted to say about islands. So it's quite an amazing result. But this is also all I wanted to say about it. Because I still want to discuss one other thing, which is in the Lauquix-Malacena derivation, we have these cigar-shaped pictures with, in the end, you have the RT formula as in the form that the entropy is given by the area of this Zn fixed point sigma, the one that minimizes its area, over 4G. But sigma is the tip of the cigar. And so these pictures, it might not be completely clear how those pictures relate to the standard picture you know of the RT surface. So this is the one thing I still wanted to add. Okay, and for that I want to go back to the simplest region case, which is the one with just a simple interval. And that's the one that we can map to thermal system. So, specifying again to simple region where A is an interval, we have that SA is given by the area of the minimal surface over 4G. But in this U1 symmetric case, meaning it can be mapped to a thermal system, which is exactly what we did, it's equal to the area of the horizon of the non-replicated bulk solution over 4G. So with the horizon sigma being the point RSR plus, which is a codimension 2 surface, so a line in our 3D bulk. So let me here indeed draw the picture. The type of pictures that we draw in the Laukemix-Maldacena derivation. So our U1 so our Zn fixed point in this case is also U1 fixed point because we're working with a simple region. U1 fixed point we called sigma in Laukemix-Maldacena, but it really is just the horizon of the non-replicated system. And so for that, we know that just let me add one further formula here, which is so that the area is equal to delta xz times r plus over 4g. So the horizon is the line of points at r is r plus. And so depending on whether we're working with the BTZ black hole, in which case delta xz is 2 pi, we have a finite RT surface with the length of the geodesic being 2 pi r plus. Or in the case of the BTZ black string, this is actually infinite. Okay, so this is because we're in the thermal picture where our region A has already been moved to be the full XZ region of a cylinder on the back. So this is where we drew our A. So originally we started from the setup where we have an interval A in some CFT, and we can conformally map it. There was a step in between in our conformal map where we mapped it to the infinite half-life, like this. And we did some conformal maps such that this simple region, being an interval, could be mapped to a thermal system. And that thermal system has a smooth ADS dual, which is just the BTZ black hole. And that one we drew as the solid cylinder. So if this is a thermal CFT geometry spanned by the spatial direction of the cylinder and a periodic Euclidean time direction tau, then we had this picture on the board before where this is A on the back. And if you now consider the solid cylinder, that solid cylinder ends in the point r equal to r plus. So as you go to smaller values of the holographic direction, you're considering smaller and smaller concentric circles until you reach r is r plus, which is your horizon radius, right? And it's slices of this picture. If you take a slice here, and you only draw the r tau directions, and you suppress xz, then these are the LM type pictures that end in some point sigma, which is in this case r is r plus, your U1 fixed point, and your boundary has a 1 times 2 pi or 1 times beta periodicity. So this is an r tau slice of this solid cylinder bulk dual of our thermal interpretation of the entanglement setup. Yeah, the first one that we encountered. Good, so this geometry here in the bulk is this BTZ geometry. Let me write the actual ds squared. So the solid cylinder has 3 directions, x, z, tau, and also this extra holographic direction r going into the solid cylinder. So it's in this column of the thermal description of our original setup that these Laukwix-Maldacena pictures live. They are sections of the holographic dual of this interpretation. And so if we want to go back to the holographic dual of this original setup, we just have to track back these conformal maps that we were doing, but on the bulk side. So here we had some conformal maps in the boundary. And these conformal maps on the bulk side, they just correspond to bulk coordinate transformations. And the explicit ones you can find, for example, in Cassini-Huerta-Myers, who wrote down the explicit corresponding bulk transformations to these conformal maps. And so if we track them back, then we just have, what we should have, of course, is that the bulk dual of this two-dimensional CFT, which is not thermal, is just a vacuum ADS bulk, or a planar ADS bulk, rather than a black hole ADS solution, which is dual to the thermal cylinder. So here we have, we called it TE going up like this, X going like this. And then we have, again, if this is a picture of the zeta cylinder, then large Z is your holographic direction in these coordinates that takes you into the solid cylinder of the holographic dual description. Okay, so here our ds squared for ADS is 1 over Z squared dZ squared plus dTE squared plus dx squared. So I'm in Euclidean signature for all these. And so you just have to do some bulk coordinate transformation to go from these coordinates, TE and X, to tau R and XZ. So if I add A here on the boundary of the ADS solid cylinder, then I have A somewhere here, okay. And then in the picture in between, I've sent A to be half of the system. I have A to be something like this. And then at the end, okay, this is supposed to be a straight line. I have this. And so it can help to look at a constant time slice of this ADS cylinder. In both types of coordinates. So once the large Z and X, and once using R and this XC, okay. So ZX coordinates, a time slice. So I'm looking at a time slice there. In ZX coordinates, circles of constant Z would look like this, where X runs from minus infinity to infinity here. So going all the way around. And in R XZ coordinates, a time slice looks like this, where this line is R plus. This line is xz equal to 0. This is xz equal to some constant and minus that constant. So here in this point would be xz is infinite, xz is minus infinite. So that the full range of xz only covers 1/2 of the whole thing. And constant R lines are like this, okay? So this is R to infinity. You go into the bulk and you end at R is R plus, and then there's a second copy like this. So with this picture in mind, we can now draw the RT surface, knowing what it is on the right-hand side and tracking back to the left what it is in our original picture. Namely, the whole point was that the reduced density matrix in this picture is equal to the thermal density matrix. Therefore, the entanglement entropy for A is equal to the thermal entropy, which is dual to the thermal entropy of the dual black hole, which is given by A over 4G, where A is the area of the horizon. So the horizon in this case is my U1 fixed point sigma, which is a special case of the Zn fixed point sigma of the more general Laukowitz-Maldacena derivation. So the RT surface in this case is my horizon. R is R plus. This is my RT surface. And now I'm going to track back in the bulk using the Cassini-Huerta-Myers bulk transformations, which are dual to these conformal maps, where R is R plus will end. R is R plus is this line on the constant time slice. So on this constant time slice, it's this line that cuts the slice precisely in half. This is the R is R plus line, such that indeed it connects the endpoints of A now. And then tracking it back further, it has to be the blue line that connects to the endpoints of A. So I've tracked my RT surface from being this horizon to, in fact, being the geodesic like you would typically see in RT pictures, which is the minimal geodesic that is homologous to the boundary. And this is just what I wanted to add so that if you have this RT picture in mind, you understand how it's connected to these LM pictures that we've been working with in derivation. I think really that's all. So I also have the Lorentzian version of those pictures. So if this first line is the Halsey trick of mapping your CFT problem to a thermal description, then Cassini-Huerta-Myers discussed the holographic interpretation of that. And it's a special case of the LM derivation of this morning. And so in Euclidean signature, these are the pictures. In Lorentzian signature, there's also a Poincaré horizon, but and in those pictures you can see that the region between the RT surface and the boundary region A is what indeed is called the entanglement wedge, and it maps to the region that the Schwarzschild, one-sided Schwarzschild observer in ADS has access to. What else did I have to mention here? Right, so one more thing is that from these mappings, it's clear that what we called the Zn fixed point, namely sigma, in the end, indeed attaches to the Zn fixed points of the boundary, which were at dA. So the Zn fixed points of the boundary do extend into the Zn fixed points of the bulk. So Zn fixed points sigma in the bulk extends to the Zn fixed points dA in the boundary. So if you would put twist fields again, then they would be along all of this. If you would put twist fields again, you would put them along all of this blue line. So these are the boundary fixed points, and in the bulk, they are on the sigma surface. So I'll have to stop there. I have some problems that I could write, and if you're interested in the solutions, I can give you a quick version of those also. But yeah, in the end, it made more sense to also discuss some more of the holography things. Questions? Yeah.
You said that you can do the bulk coordinate summation and go from ADS to the PTZ. That's, I guess, basically the state of PTZ is locally ADS, so you can use this coordinate summation.
Right, yeah.
A higher number of dimensions, you can have ADS elliptical black holes that are not just locally ADS, right?
Yeah, so here indeed I'm doing the 2D, 3D thing again. That's right. So this really is only true also for the BTZ black string, which is the one where XZ has this full range, and so if you go to BTZ black hole, which is in fact different from the ADS solution globally. The reason it's different is because then you do these identifications. Here at XZ is minus pi and XZ is pi, you identify these two lines. And that makes a BTZ black hole, which is then different from just being locally ADS. So this was true in these specific cases, but Cassini-Querta-Myers do discuss the d-dimensional case. I think in the same way that so d-dimensional CFT, in the same way that Laukowicz-Maldacena also do that, which was on the board this morning. That you can just drop that conformal factor, so there is a conformal transformation that you can find, and yeah.
Can you verify the names of the authors of this paper?
Yeah, sorry. Uh, 2011, sorry, maybe 1102.
How to interpret these islands physically? Because I guess whenever we've been constructing these replica manifolds before, it's always been the regions that get glued between the copies.
Yes, yeah.
Are always the parts that the observer has access to, right?
Yeah.
You said this island thing appears as some feature of some other saddle point in the solution. So how is that related to this interpretation of this observer interpretation?
Yeah, the idea is that gravity is able to come up with a solution that has this feature that those replicas are connected through such a wormhole solution. But what you're calculating is still the entropy of the radiation region. So this R remains your A, where you put an observer. So this is the guy who's, or the observers whose entropy we're interested in calculating. So it's not really so, not that according to my understanding, that there's an observer associated with the island region. But in the pictures of the replica manifold, it makes sense to introduce an island that plays the same role of R, in the sense that this is where the replicas connect in that gravitational region. But I'm not an expert. I don't know if there's.
I think there's something. This was part of Engelhart and Wall about the generalized entropy, the QES, and generalized entropy being just outside the Ringler wedge. So the Ringler wedge is what is accessible to an observer on the boundary. But then when you add this entropy term and take it into account when you minimize when you minimize the generalized entropy instead of just the area to find the QES, it puts it a little bit outside of the Ringler wedge. So even before you have an like island, you have something that's not completely causally related to the boundary. And the difference for, is like order G is what they say in the paper, but here it's obviously much bigger because there's like a lot of radiation. And so there's like when you interpret the RT formula in terms of quantum error correction. So this is like there's a paper by like Carlo after his papers by Almieri and Dong, right? There's a theorem that's like you can reconstruct everything in the entanglement wedge from so like it's sort of the idea is like it's known that, or it's known, or I don't know how well known that you can reconstruct things in the entanglement wedge, but interpreting in terms of the observers is weird.
We should talk about these
Yeah.
Thanks.
Thank you. Yeah. So we should move on with the, or do we have a break?
We have a short break.
Ah, yeah.
Yeah, 5 minutes, but first, since that was the end of your lecture,
Right.
again.
Thank you. Yeah, and thank you all for attending and for the questions and the attention. Thank you.